So, good afternoon, everybody. My name is Rodrigo Sierra, and as you have heard, I'm coming from CERN in Geneva, a physics center, where we are using LoRaWAN for many things. I won't talk about millions of devices or about national deployments, but you can use LoRaWAN for some exotic areas as CERN. So, just a couple of words about CERN. I suppose you have heard at least the acronym once in your life. It comes from 52, so you have to think about Europe after the war. A group of visionaries thought that it would be a good idea to have a center of excellence for physics in Europe. And then in 54, a couple of years later, the idea was endorsed by 12 countries, and the European Organization for Nuclear Research was born. So we are exactly 70 years later. So other than celebrating our anniversary, CERN has grown. We have still the same will of looking for the unknown. But we have now 23 member states. We have 11 associates, and some of them are in the pre-stage to become a member. So even if we are called European, the organization is becoming a world endeavor. So we have collaborators for around 600 institutes for 70, 80 countries. So I mean, it's a worldwide effort. Instead of personnel, we are 2,500 staff. We have students, we have fellows, we have contractors, of course. But our main community of users are the scientists that come from all around the world to work with us. And they come mainly because we are the biggest laboratory for particle physics. You have a view from Google Maps of CERN. So the big circle is the LSC, is our biggest accelerator, and you can see on the map Geneva's lake and the airport to see the scale. We are still doing the same than 70 years ago. Our mission is to perform research on particle physics. So in the 50s, it was called nuclear research because I mean we were looking at the nucleus. Today we prefer to call particle physics because we go smaller and smaller. So in 20 minutes, I won't go into the slides because I mean it can take several days of discussion about what does this mean. But well, it's our vision. So I mean, if you want to know a little more, go to cern.ch. You will find tons of information. So how does it work? So we look for the tiniest particles, and for that we build the biggest machines. So if you, I mean, I won't enter into Einstein, but this famous E equal mc. So you want to go into the high energy, you want to have a speed. And in order to get the speed, you need accelerators. So an accelerator is just a circle, and every time the particle passes, someone hits them. Once and once and once. And the faster that the particle goes, the more energy you need to bend it. So either you have magnets that are super powerful, or you have bigger accelerators. And that's why over the years, you see that accelerators pass from 100 meters to a couple of kilometers, 7 kilometers, 26 kilometers, bigger and bigger. And then what we do with the particles, we just collide them. We smash them, and we look what happens. And for that, we need cameras. But the camera for us is a detector that makes 10 floors and makes several millions of pictures per second. So we have huge installations just to see what happens with the small particles. So how does LoRaWAN fit on all this? So this is a footprint of CERN. So basically it's around 60 square kilometers, the campus. And we have around 1,000 buildings, between buildings and barracks. We have a lot of galleries, of course, and some specificity, all the physics is done under the ground. So all the accelerators are underground facilities. And because of the nature of the particles, we have radiation when the accelerators are running. So it's quite a specific environment. In 2019, we are in an industrial environment, and people come to me telling, okay, we have some use cases where your wireless networks do not fit. So they were looking for something that LP1 could solve. So we started to take a look. We had some discussions, and at the end, we decided to deploy a private LoRaWAN network. So we have everything private on premises, and we have deployed everything ourselves. So we started to put some outdoor gateways in the strategic points to cover more or less all the campus. And since we already had all the building blocks, we have a big IT department, we have a big industrial environment with all the tools. The first thing we made was integrate everything with our tools. I mean, we have discussed this morning about it's not technology as a service. If you don't give to the user the tools that they are used to work with, it won't fit. So I mean, we gave to the users all the integrations with the IT frameworks, with the industrial frameworks. So the work orders are automatic when the sensor is out of battery. All the pipeline for data is the same they have for other sensors. I mean, everything is done so the end user has exactly the same environment, independently of its LoRaWAN or other things. So instead of use cases, I mean, I've taken this picture a couple of weeks ago for the presentation from the water tower. You can see that it's a normal industrial environment. We have hangars, buildings of metallic, concrete, offices. We have a kind of everything. So on surface, it's a normal industrial environment. Underground is another stuff. So we have the typical use cases you can find in an industry. We have temperature, humidity, I mean, asset tracking. Something that we started that was a little specific already, it was radiation waste monitoring. So currently, when you go to CERN, they have some plates on the side. Nobody knows what it is. In case there is some radioactive waste that goes outside the premises, it starts to beep, and the UR stop. It shouldn't happen. It's accidental, but accidents happen. So in fact, my colleagues from radio protection say, OK, why not to put some sensors on the waste containers, as if something happens, we will know it on real time instead of waiting for the waste to go out. So it was one of the first LoRaWAN use cases that we got, is to put sensors on the bins that measure the radiation. If something happens, says hello. Then we have other, let's say, typical cases. We have every kind of industrial vehicle that is self-service. We have cranes, forklifts, every kind of, I mean, we are a big campus. So we have put the LoRaWAN sensors on them. So I mean, for the people doing the maintenance operation and to see also the usage is quite handy, because before, I mean, it was just go and find it. And also an interesting use case, because I mean, I think everybody likes to hear about return on investment and things like that. We have 400, 500 cranes of all the sizes and tones, etc., scattered around the campus. So this picture is just to give you an idea how an experimental area looks like. You have the crane at the very end of the picture, the yellow line that you cannot see. And since physics is quite dynamic, when they change the experiment, they put concrete box to protect the surrounding area from radiation, and they move it quite often. So we have this kind of cranes all around the campus. So what our colleagues made, it was just they put the LoRa sensor on LoRaWAN sensor on them, and they measure the activity and the time of the day. So in fact, the maintenance is now on the real data and not on a yearly basis. So in 1 year and a half, the investment was already returned, and everything they do from now on is just gain for it. So these kind of cases that you can find in industrial scenarios, we have in CERN, of course. But also we have something a little more, let's say, exotic that we have to use LoRaWAN for. So I suppose you have also heard about COVID. If someone has not heard about COVID today, raise the hand. So of course we couldn't telework, all of us, because during the COVID times we have to still run physics. So we have several thousands people in the campus working every day. And by law, we had to follow the rules. So we had to track the contacts of people, because we are in 2 countries. We have half CERN in Switzerland, half CERN in France. So we have 2 laws, 2 different scenarios, 2 different. So even an application from one country didn't work on the other. So we developed our own solution that it was called a proximeter. It was quite. So basically, what we made it was measuring if some people were too close for a certain period of time. It vibrates in case it happens, so you go out. But also, it alerted the medical service. So in case one of these people was infected, then automatically every people who was in contact with him received a message from medical service. So technically, it was ultra-wideband that we used for measuring the distance, but we needed the technology in order to go up all the messages. In a campus that is 6 square meters, we have roads, we have, so it's not only us, it's also all the roads in France and Switzerland in between, and all the areas. So in fact, LoRaWAN was a perfect candidate in order to use it as a SNLP solution. So we implemented the LoRaWAN solution within the proximeter. So every 15 minutes, it sends uplink whatever message they have to send. But since it was safety, because I mean, health was involved, we have to acknowledge every message. So we finished at the end of the day that at between 8 and 8:30 in the morning, 10,000 people were joining the network. And at peak times, so lunch, re-meetings, etc., we have bursts of several thousand messages coming on the same place at the same time. So we had to densify quite a lot the number of gateways in specific places in order to comply with the duty cycle, but also to be sure that we didn't lose messages because it was the health of the people who was there. So. And then we thought, okay, I mean, our business is physics, and physics happens underground. So why cannot export LoRaWAN into the underground facilities? It will be quite handy. So I mean, control, and I mean, everything is already done for the accelerators. But if you want to measure something because something happens, or you want to make some preventive maintenance, you cannot do anything today because we have radiation on the accelerators. So basically, when the beam is on, there are some particles that don't behave as they should, and it impairs electronics. So every electronics that is not specifically done for radiation environments will die within hours. So we cannot put anything commercial if it's not specifically component in the accelerator because it won't live long. So we have some areas in the underground facilities where we can put equipment, but if you see on the picture, this is the LSG. There are some small dots. It's every 1.5 kilometers. So I mean, you have a sensor need in the middle of the arc, and you have to put it 1.5 kilometers away. It's kind of useless. So what we did is we developed our own solution. So we have a radiation-tolerant LoRaWAN platform. I put some links if someone is interested on how to harden LoRaWAN. There are some links at the end of the presentations. But basically, it's a platform that uses LoRaWAN. It has been hardened by hardware and by software. So in fact, it can resist radiation. So we can now put a sensor anywhere in the accelerator chain, and it will start sending data automatically. From the network point of view, we have 65 kilometers of accelerators, or 60, 65, and we cannot put any electronics. So in fact, we have to cover up to 1 kilometer, 1.5 kilometers for the injection point. So basically, we use, as in many tunnels, radiating cables. And we are limited to a certain frequency because the distances to follow, so otherwise the propagation are not enough. So in 2021, we decided to make a pilot. At the same time, we were developing the radiation-tolerant platform. And we realized that, I mean, putting LoRa in the middle of all the technology we are injecting on the cable fit well. The results were quite positive. So now we have today 45 gateways covering all the accelerator chain. What's the outcome? So basically, in the past, either you have a radiation-tolerant device with no connectivity, so you have to wait 6 months sometimes in order to get the data. Either you have the field bus, but you have to install it, and you have to have electricity, and you have to pay for it. And with the LoRaWAN platform that is resistant to radiation, if you need something, you install it. In 2 seconds, you have data 2 seconds later. So knowing that we can access accelerators twice, 3 times per year, so we had 2 days last week. Next time we can access is in September, and this is Christmas. If you have to wait 6 months to get your data, at the end, people didn't install any sensors. So now that we have the platform, the first thing, the driver of this platform was the radiation monitoring levels on the accelerator chain. So in the past, it was 6 months to 1 year in order to get one sensor, and it cost 30,000 euros to install one. Today, we have only one LoRaWAN sensor. We put it there. I just taken a picture of how we have just put it over the accelerator. And in 2 minutes, the device is installed. So basically, the installation process, the cost has been dramatically reduced, and hence the number of points where we can measure is infinite. I mean, we can put as many as we want, as fast as we can. So then, once we have opened the box, then we can do anything. I mean, we have 60 kilometers of tunnels. Some of them dates from the 50s. So we start to have cracks, displacements. In the past, there were some measurements that were done, but we cannot access the accelerator, a person either, during 6 months because the beam is running. So in fact, we put something, we measure it later on. So today, we can start to put sensors for ad hoc monitoring whenever we want for whatever we want. Vibration, electromagnetic, think about something. It's what I tell my colleagues. Now you can do whatever you want. It's just a question of having the idea. So now we start to put everything that is industrial on surface. We are able to do it in the accelerators. And before it was just not possible. Or super expensive either, day one. So basically, we have deployed over the last 5 years a quite robust LoRaWAN solution. It's a service. I propose in the service is up to the user to know if the return on investment for his use case is worth. We have opened it for accelerators, and it has been. We have opened the melon. It's now out to the accelerator sector to use it because they are quite happy that we have a solution for them. And also, LoRaWAN is there. If you have any kind of need, you can use it. The COVID proximeter was one use case that it's perfectly showing that you can integrate it into any kind of solution, and you can use it for that. So. Some lesson learned. Well, we have discussed about service this morning, so I have not put it here. You need to offer a service. You cannot offer just like technology because it won't fit. But what we have learned ourselves also at CERN, we have a lot of concrete and a lot of metal. Because of if the radiation cannot go out, the propagation of the radio waves do not go in. So we have a lot of Faraday cages. And also, people start to use LoRaWAN quite a lot on different, let's say, levels of confidence. I have put a gateway, a couple of them in the water tower. I receive several thousand messages per minute on the same frequency, on the same spreading factor, from the same device. So you cannot fight people who misbehave or devices that misbehave. So you have to control your network and your infrastructure. So you fight against the other with solutions. So now we are at the moment of when the technology is there and when people start to use the service, we have to be sure that we offer a service that is worth instead of network and service. So I put you at the end of the presentation several links. So for those who are very interested about CERN, about how to harden LoRaWAN or how to use it in accelerators, I don't think many people have accelerators at home, but if you can read. I won't go further on it. So thank you very much.
Right. Does anybody have any questions for Rodrigo?
Back to the COVID application. How did you come to the conclusion that you needed to densify the network based on traffic?
Sorry, can you?
How did you conclude to densify the network based on traffic?
So I made some purely mathematical calculus, and also we checked the statistics from the gateways we had, and then we have to densify because people are, let's say, people behavior, you can predict it. So at the end, we finished putting gateways on restaurants, on control rooms, in front of the tram, in front of the bus, at the entrances. And at the end, we make, at network level, we scatter all the downlinks between the different gateways, and we multiply by factor 2 every position. So we have a geographical redundancy. And then the outcome was at the end, we were okay on that. But the problem we had was the bursts. People arrive at the same time, leave at the same time, do everything at the same time. So.
I think we have time for one more. Yeah, Paul.
Yeah, hi. Enjoyed having lunch with you today. What were the top 2 challenges you had in building your LoRaWAN network at CERN?
So the biggest one was the radiation. So it has taken us some years of development for hardening everything. But also, I was telling you before, our big problem is the structure of CERN. It means nothing can go out. So what I wouldn't like to have is one gateway per building, because then the use case is completely, it doesn't make sense. So now what we are trying to do is, to have an indoor coverage idea, so we can also tell the users, okay, this is what you can get, and if you need some specifics, come to us, and we can put some specific places for indoors or to densify. But in some areas, either we put a gateway in front of the device, or nothing happens. So I mean, in terms of cost, then it can increase. I will be at the very end if someone wants to discuss our physics. You are welcome.
Right. Well, living proof that every segment of society can be digitally transformed by wireless LoRaWAN connectivity. Thank you ever so much for a really insightful presentation there from CERN.